Good afternoon, guys. How's it going? Mike coming back at you with another video on college algebra. In this video, we're going to begin a new chapter, and we're going to talk about a way that we can make solving systems of linear equations easier. We're going to talk about these things called matrices, what they are, how we use them, and what we have to do with them to solve them, and in the process, do something related to systems of linear equations, and then later on in the chapter we'll talk about more properties of matrices and other things we can do with them. But if we look at a system of linear equations, either in 2 variables, 3 variables, we can actually do this with however many variables we want, but for the sake of actually doing practice problems, we're going to stick with systems of 2 equations in 2 variables, or 3 equations in 3 variables. If we take the coefficients of the variables in our system and we put them into n array, typically a rectangular array, we create what's known as a matrix. And if we include the column of values that each equation is equal to, we have what's known as an augmented matrix. So here, just to show you what the heck I mean, here's a system of 2 linear equations in 2 variables. I have x plus 2y equals 4, and then 3x minus 5y is equal to 1. This system has matrix 1, 2, 3, negative 5. And note that we took the numbers in front of the sort of corresponding pieces. 1x, there's the 1, 2y, there's the 2, 3x, there's the 3, and then plus a negative 5y, there's the minus 5. If I include these 2 numbers here, the values that each of these things are equal to, that gives me my augmented matrix. 1, 2, 4, 3, negative 5, 1. You just take the corresponding coefficient and put it in its corresponding place. Now, some vocabulary, some notational kinds of things that you'll see later on in the chapter, but I'm going to introduce it now so it's not so brand new once you see it later on. This matrix here, 1, 2, 3, 5, 1, 2, 3, minus 5, sorry. We call this a 2 by 2 matrix. When we refer to a matrix, we always refer to it by the number of rows that it has, followed by the number of columns. So this matrix has 2 rows and 2 columns, so we say that this is a 2 by 2 matrix. This matrix right here, the augmented matrix, would be a 2 by 3 matrix. We have 1, 2 rows, and then 1, 2, 3 columns. So that's just a little bit of some terminology, some notation that you'll be seeing later on. There is a word for this. It's called the order of the matrix, but we'll get into that more later on in this chapter. So this is an example of taking a system of linear equations and turning it into a matrix. You should be able then to go the opposite way. If you're given a matrix, specifically an augmented matrix, you should be able to look at the matrix and then write the system of linear equations from that augmented matrix. So if I go 2, 3, 4, 5, 6, 2, if I had to write this as a system of linear equations, knowing that this is an augmented matrix, this last column here, those are going to be the values that your things with x's and y's are going to be equal to. So this is saying the same thing as 2x plus 3y equals 4, and 5x plus 6y is equal to 2. Nothing too complicated happening there. Sometimes, to be more clear that it's an augmented matrix, some books you'll see put either a solid vertical line or a dashed vertical line before that last column. This is just one other thing that they can do or use to show that this is the augmented matrix. So when we're solving systems of linear equations with matrices, we're always going to be working with the augmented matrix. You don't have to worry about this thing here. We're always taking the coefficients on our unknowns as well as the numbers that those things are equal to. And we're going to be doing some operations with the rows of these matrices to help us solve a system of linear equations. There's three main operations that we can do. They're called the elementary row operations. And here are the three things you can do. First thing you can do is you can switch the location of two rows. So using this same matrix, 1, 2, 4, 3, negative 5, 1, I can switch rows 1 and 2, and it works just as it sounds. Row 2 becomes row 1, row 1 becomes row 2. And when we do some kind of operation with the rows in our matrix, we do specify what is being done. And we do draw arrows from one matrix to the next to show what operation is being done. If you want to switch two rows, we do R1 and then an arrow pointing both ways, and then R2. The second thing we can do is we can multiply a row by a non-zero constant. So here I chose to take the entire second row and multiply it by a 3. The first row remains the same because we didn't touch it. The second row is the only thing we messed with, and you just simply multiply each number in the second row by 3. So 3 times 3, 3 times negative 5, and 3 times 1. 9, negative 15, and 3. And then the third operation we can do, this is perhaps the more complicated one, or the most complicated one, is we can add a non-zero multiple of a row to some other row. So what I did here was I took 2 times row 1 and I added it to row 2. That's the 2r and then the little 1 subscript plus r2. Now we do have to specify here what row are we going to change, because I could do 2 times row 1 plus r2 and have that take the place of row 1, or I could have that take the place of row 2. So how do we know, or how do we write what row we're actually changing? That's why I have the arrow here and then the r2. This here says that I am taking 2 times row 1 and I'm adding it to row 2, and that is going to become my new row 2. So row 1 remains the same because row 2 was the row that we were changing. 2 times 1 is 2, plus 3 is 5. That's why our new entry here in row 2 is 5. 2 times 2 is 4, plus the negative 5 gives me negative 1. And then 4 times 2 is 8, plus the 1 gives me 9. So it's 2 times each of these numbers plus the number underneath it. That gets you the new 3 numbers that are making up your row 2. So those are the 3 elementary row operations that we do with matrices. We want, in the end, we want our augmented matrix, after using these elementary row operations however many times we may need to, we want our augmented matrix to be in what's called row-reduced echelon form. or for short, as you'll see it later on in the video, RREF. We say that for short because row reduced echelon form not only becomes a pain to write after writing it so many times, it also becomes a pain to say after saying it so many times. So what is this row reduced echelon form? A matrix is in row reduced echelon form if four things are happening. First thing, all rows consisting of all zeros are at the bottom of the matrix. They are the last rows in your matrix. For all other rows, the first non-zero entry in the row is 1. And this 1 is called the leading one. 3, the leading one in each non-zero row is to the right of the leading one in the row, immediately above it. And fourth and last, each column that has a leading one in it has zeros for all the other entries of that column. So all four of these things have to be happening for our matrix to be in row-reduced echelon form. The matrix at the left here is an example of a matrix that is in row-reduced echelon form. Any rows, if there are any, that would be all zeros would be at the bottom, but there's not, so we don't have to worry with that. The first non-zero entry in each row is indeed a 1. 1, 1, but there's a 0 here, so that's fine. 0, good, 0, good, 1 there, we're good. The leading 1 in each non-zero row is to the right of the leading 1 in the row, immediately above it. Go up 1 row. Oh, this 1 is to the right of that 1. Go up 1 more row. Oh, this 1 is to the right of that 1. So that's fine. And then fourth, also each column that has a leading 1 in it has zeros for all the other entries in that column. Leading 1 in here, the other entries are zeros. Leading 1 here, other entries are zeros. Leading 1, other entries are zeros. So that is an example of a matrix that is in row-reduced echelon form. The matrix here is not in row-reduced echelon form. We don't have any rows that are all zeros, so that's fine. We do have that the first non-zero entry in each row is 1. We do have it so that the leading 1 in each non-zero row is to the right of the leading 1 in the row immediately above it, so that's fine, but number 4 fails. We don't have it so that in every one of our columns that has a leading 1, all the other entries in that column are zeros. That's not happening here. So this is now what we want. We want this to be in row-reduced echelon form. So once we have a matrix in row-reduced echelon form, earlier on in this video, we did mention that we should be able to take a matrix and then turn it back into a system of linear equations. And this whole process here is known as Gaussian elimination. Gaussian, the first part of that, Gauss, comes from a very famous mathematician, Carl Friedrich Gauss. If you want to learn more about the history of math, I suggest you look that up on your own. Not going to spend time on that here. But if you're given a system of linear equations, again, for our purposes, we're sticking with 2 equations in 2 variables or 3 equations in 3 variables. We're going to first write the augmented matrix for the system. Very easy. We saw how to do that at the beginning of this video. Step 2, we're going to use our elementary row operations to take that matrix and put it in row-reduced echelon form. This is the part that's going to take some time. This is the part that takes some practice. Doing these things by hand can get a little bit tricky, but once you get used to it, it's not bad. And then 3, you're going to write the resulting system of linear equations, which you're actually going to find out is a solution using that row-reduced echelon form matrix. And the idea here is that comparing the matrix you created in step 1 with the one you get at the end of step 2, those matrices are equivalent in the sense that the solutions you come up with are indeed valid solutions to the system that you were given to begin with. So that concludes this video for now. In the next video, we're going to do some sample problems. We're going to see how we use these row operations, and we're going to actually solve some basic systems of linear equations using Gaussian elimination. So guys, if you have any questions or comments, please be sure to reach out to me. Emails, phone calls, rocks through my window, carrier pigeons, messages on blimps over the Orange Bowl on New Year's Day, whatever you have to do. Otherwise, until the next video, take it easy.